Hello, my name is Eunji Yu from PostTech in Korea. This time, I will introduce my paper, TF MVP, Novel Sparsity-Aware Transform Accelerator with mixed-length vector pruning. Let's get started. As you know, Moore's law has doubled its performance every 2 years, and CNN has increased 15 times every 2 years. With the advent of transformer, it's super going up 750 times in 2 years. We need hardware-saving technology to train and inference to it. Therefore, model compression techniques have been actively considered as inevitable procedures, reducing the model size for practical memory footprints. Among various approaches, pruning has been regarded as an effective method to make a compact yet still accurate transformer model by removing as many less important weights as possible. Combined with fine-tuning procedures, the pruning-based weight sparsity is a popular method for reducing model complexity while maintaining the original model accuracy. The pruning method generates a masking matrix for each weight matrix to represent less important weight positions, and the unpruned weights are obtained by collecting non-zero weights after performing Hadamard product of masking and weight matrices. And then we will prune total 4 parts. 2 are located in multi-head attention layer, and others are in feed-forward network layer. But unfortunately, unstructured pruning causes irregular patterns and has difficulty with parallel operation. Due to that, mag utilization is decreases, and we got the result in low hardware efficiency. So, just pruning cannot accelerate hardware directly. To solve this issue, we should find a great structured pruning that maintains high quality, and also need to develop a pruning-aware transform accelerator, including sparsity-aware engine. First of all, to find great structured pruning, we analyzed the masking matrix from the previous work on structured pruning. As you can see, there is a shape and it will be captured as a structure. If you look closely at the multi-head attention, this shows the masking pattern of the first and second matrices in the multi-head attention part of the fourth layer for GPT-2 small when the average pruning ratio is 0.8. Since the operation of the transformer itself is based on has in the multi-head attention side, it can be seen that it has a stride pattern based on QK and V has. As the value becomes darker, it means that the corresponding area is preserved. And as the value becomes lighter, it means that the corresponding area is pruned. Also, although it is not a perfect at the head level, it can be interpreted that there exist some has that are particularly important. Furthermore, the directions of GPT and BERT are slightly different in the fully connected layers. The first matrix of the fully connected layer is displayed, and it can be seen that GPT-2 shows a pruning shape with a slightly horizontal line, while BERT shows a vertical line, which makes sense when viewed as an encoder and decoder. This is the result of fine-grained movement pruning that generates random sparsity without structure. Therefore, this can serve as a best baseline for pruning. But since patterns exist, I got the motivation for structured pruning. We named it mixed-length vector pruning, and the story is simple. First, we obtained the pre-trained dense version of the transformer, and then we perform fine-grained pruning through the movement pruning mentioned earlier. We analyze these patterns to obtain direction strength, which quantifies whether the direction is strong in the horizontal or vertical direction, and the degree of strength. Based on this, we determined whether the corresponding matrix should have a vertical or horizontal structure, and what length the vector should be when it has structure. Then we proceed with structured pruning according to the direction strength. we continuously generate a finer weight matrix during retraining. Of course, in this process, we have made the original baseline for pruning start from the pre-trained model. In order to perform structured pruning, it is important to define how to obtain the direction strength. We have defined the vertical or horizontal level strength by statistically analyzing a matrix where the white color represents a value of 1 and the black color represents a value of 0, indicating the surviving weights patterns after fine-grained pruning. We calculate the difference between the averages of the horizontal and vertical directions based on the variance of the values. Based on the matrix M on the left, SV and SH are 0.49 and 0.32 each. If you subtract SH from SV to get the direction strength S, we get positive 0.17, and this means that it is horizontal vector level pruning. In case of vertical vector level pruning, as you can see, direction strength S is negative value and degree of the strength is 0.17. Although the formula is not perfect, we have found that the variance can provide useful information. The greater the line strength, the greater the absolute value of the direction strength. Using this direction strength, we analyzed 4 matrices for each layer of GPT-2 small under the condition of pruning to 0.6. As we observed earlier, the matrices clearly show the patterns of horizontal direction in the attention part and vertical direction in the projection part. Similarly, in the fully connected layers, we can see the patterns of horizontal and vertical. Based on this, we set a threshold on the direction strength and performed structured pruning with a vector length of 4 within the range. And as the threshold is gradually increased, the vector length size is also increased. Larger vector lengths increase efficiency at the hardware level due to stronger structures. Therefore, we aim to provide the highest possible vector length while minimizing accuracy drop. And here is an example of transformer layer number 5 of GPT-2 small. If you look closely, MHA attention and first FFN are horizontal direction, and MHA attention's vector length is 16, since it has a relatively high direction strength. And first FFN's vector length is 8, and other values are given in the same way as above. We also conducted a similar analysis for BERT. In the case of BERT, we can see that the plus and minus patterns show a different tendency in the fully connected layer compared to GPT. There is only MHA attention in the horizontal pattern, and others are in the vertical pattern. Based on this, the concept of mixed length vector structured pruning can be applied in the basic pruning process. Here is the various conditions of pruning method with pruning rate from 60% to 80%. As we increase the pruning rate, we can see that the performance drops. First, head level pruning has a drawback of not being able to achieve high pruning ratios because pruning is only performed in the attention layer. Even so, the performance drop is significant. So it is not a sensible solution to eliminate entire heads at the head level. In the proposed approach, when we perform pruning with mixed vectors, we can achieve results that are almost similar to the fine-grained results. While previous works only used one direction, such as row-wise pruning, this work chooses vertical and horizontal directions based on the matrix characteristics, thus defending against accuracy drops. From now on, I will suggest a dedicated transformer accelerator fitted in mixed-length vector pruning. This architecture is based on paper Optimus Accept MRCs 20, which matches sparsity-aware and load-balancing transformer accelerators to advance our work. First, there are 2 parts, memory part and computation part. As you know, memory part has input and wait memory and also has the external memory DRAM. And we will focus on computation part in this presentation for sparsity-aware and load balancing. For this, we propose the following three. We do pruning on a vector basis, and it can be packed a group size 4. So can do group indexing, and it makes be an efficient global input buffer. In addition to supporting 4 unit vectors, we also support 8 and 16 unit vectors simultaneously. To do this, we created the concept of a P group, which bundles 4 P's with 4 MAC units each, allowing for the runtime to reconfigure the 16 MAC units as a single unit to manage them. Previously, in Optimus structure, a single P was configured with 1 MAC unit to support random sparsity as much as possible. However, since our minimum vector unit is 4, resulting in a higher matching rate across a wider scope than before. Therefore, our utilization is higher by default, based on the same number of MACs. And we support dual mode for vertical and horizontal direction in this 4 MAC location. In the process, since we need to perform vertical MAC operations, the P must support both horizontal and vertical modes when performing MAC operations. To support this, we provide internal buffer or MAC operation scheduling inside the P. The MAC operator works in dual mode. As mentioned earlier, it can be considered that an adder tree that effectively calculates P-sum for 4, 8, or 16 can be made reconfigurable. In comparing and analyzing hardware performance, the leftmost structure with Optimus and fine-grained pruning mapped shows MAC utilization for a 0.8 pruned GPT-2 model for all transformer layers. Despite having 4,096 MAC operators, the utilization stays around 20%, which is inefficient. However, our proposed hardware using fixed vector 4 or selectively using 8 and 16 with mixed vectors shows 2.9 times better increases in utilization compared to the existing Optimus structure. And also mixed version is increases by 45% than the fixed version in average. In terms of hardware efficiency, as the number of MAC operators in Optimus increases from 1K to 4K, and our proposed structure also increases from 1K to 4K, the number of P decreases by a quarter because they are grouped in 4s. This ultimately plays a role in increasing the matching rate. However, there may be some extra overhead because of group level management and buffer issues, causing a slightly increases in overhead when the number of P's is small. But as the number of P's increases, the overhead is offset by a benefit of supporting at the group level. When mapping actual GPT-2 or BERT models, the average MAC utilization of the proposed work decreases as the number of P increases, but the degree of decrease is less than that of Optimus. This effect can be clearly seen in the case of 2048 MACs. Optimus has about 40% MAC utilization, but ours has about 88%, which is twice as high, and gigaops per watt is also proportionally high. As a result, although P-sum buffer and adder tree are added for implementing our ideas, we do group indexing and double buffering and got a higher energy efficiency by about 4 to 50%. Finally, conclusion. We propose novel algorithm hardware co-optimization methods. For this, find the great structured pruning pattern and newly define the direction strengths for mixed vector pruning approach. Design a transformer accelerator MVP architecture, which is added structure-oriented hardware unit. Finally, achieve the most efficient implementation for pruned transform model. That's all I've prepared. Thank you for listening.